So now we are going to discuss about the Bohr's atomic theory. So the first point is atom consists of electrons, protons, neutrons. The second point is neutrons and protons exist at the center of atom, and this is nucleus. The third point is electrons exist at the orbits or shells, or you can say energy states outside the nucleus. The fourth point is electrons are orbiting around the nucleus as like the planets do around the sun. And the fifth point is electrons which are orbiting at outer shell will be having more energy than the inner shell electrons. So now I will draw the silicon atom. Okay, why we are only concerned about silicon? Because silicon is the most widely used semiconductor nowadays. But without silicon there are many semiconductors which are used in different purposes, but like germanium, gallium arsenide. But all those things I will discuss in direct and indirect band gap semiconductors. But right now we are only concerned about silicon. So why silicon? Because there are two reasons. One is its availability, because silicon is very available to us, and the second one is silicon is cheap. So this is the main two reasons why silicon is heavily used everywhere. So right now we are only concerned about silicon atom. So silicon atom have the atomic number equal to 14. That means it has number of electrons equal to 14, and the proton is also 14. So if I draw the nucleus, this is the nucleus where neutron and protons are existing together, and these are the orbits or shells, or you can say energy levels, where electrons are are moving around the nucleus. So these shells are identified by the quantum principal quantum number, which is denoted by n, and the first energy shell is identified by n equal to 1. The second energy level is identified by n equal to 2, and third is n equal to 3, and so on. So this n is equal to principal, is actually the principal quantum number, and it helps us to identify the energy levels. So there we have 14 electrons. So how many electrons have to be put into the energy levels? That is also determined by this principal quantum number. There is a formula. So now let me rub this part, and the formula is number of electrons at nth shell is equal to 2n square. So the shell and the number of electrons, if we talk about n equal to 1, it is nomenclatured as the K shell. N equal to 2, it is L. N equal to 3, it is M, and so on. But as we have only 14 electrons, we don't need to go beyond this n equal to 3. Only up to n equal to 3 is part of our discussion. So at n equal to 1, in the first shell, the number of electron is 2 into 1 square, that is 2. The second shell, 2 into 2 square, it is 8. And in third shell, it is 2 into 3 square, that is 18. So in the first shell, we will put 2 electrons. In the second shell, we will put 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, and 2 plus 8, 10 electrons is placed, and rest is 4 electrons. So I will put the 4 electrons in the third shell. So now this is a silicon atom. So I need to mention two important things about this picture. One is the force of attraction by which this model is getting stabilized. That is our Coulomb's force of electrostatics, that is F equal to K into Q1 Q2 divided by R square. And the second thing is this first shell that is having the most negative energy level. The first energy level is the most negative energy level of any atom. And the more we will move towards the outer shells, the energy will increase, and at infinity distance, the energy of the shell will be equal to 0. The first shell is the most negative energy shell, and as we move forward, as we move outer side, then this negative value will getting lesser and lesser, and at last at infinity distance from the nucleus we get energy equal to 0. So that is why we say that outer shell's energy is always greater than inner shell energy. Because outer shell's energy is, much more negative than the inner shell's energy. So the inner shell's energy, outer shell's energy is much more positive than the inner shell's energy, because the first energy state, which is K shell, is having the most negative energy state, and L is much more positive, M is much more positive than L. So that's how it goes. So that is why the outer shell's energy is always greater than the inner shell's energy. So this is the second point I need to mention. So right now I will talk about the subshells. In Bohr's atomic theory, it is stated that all these shells, K, L, M, all these shells, n equal to 2, n equal to 3, can be divided into some subcells. So, how will I know that which shell will be having how many number of subshells? So there is a relation that in value and number of subshells, number of subshells and names of subshells. So actually, why we are talking about the concept of subshells? Because in an energy state, if we consider the energy shells in the presence of strong magnetic and electric field, then we can see that it gets splitted. The energy shells get splitted. So split it into some sub shells, but they are they are not very far away from each other. They are slightly the value of the energy of each subcells, they vary slightly from each other. So very slightly differed energy levels of subcells are present when we are dealing the atom in the presence of any strong magnetic or electric field. So actually the shells of the atom get splitted into slightly differed energy levels, and that are called the subcells of that particular cell. So the relation is, for n equal to 1, we have one subshell, and that is the shell. There is no splitting of shells, and that is named by S. If we consider n equal to 2, there are two number of subcells, that is S and P. If we consider n equal to 3, there are three number of subshells, those are S, P and D. If we consider n equal to 4, the number of subshell is 4, and that is represented by SPDF. So, and if I draw the atomic model once again, considering the subshells right now, then if this is the nucleus, this is our n equal to 1, which is S. Our n equal to 2, I mean the L subshell is splitted into 2 subshells. So n equal to 2, we have 2 subshells, one is S, one is P. In case of n equal to 3, it gets splitted into 3 subshells. So the KLM, so the M shell is splitted into 3 subshells. It is S, it is P, it is D. The fourth shell, that is N shell, it splitted into 4 subshells, which is S, P, D and F. So right now we need to know how we will put the electrons within these subshells. What is the relation, or is there any kind of formula through which we can put? Otherwise, how could we know that in which subshell how many electrons will be present? So that is our main deal. In the next part, we will talk about orbitals right now. So if we apply a more, stronger, what can I say? If we apply a stronger electric and magnetic field to the atom, then all the subshells which we are talking about right now, they also get splitted into some orbitals. They are splitted into some subdivisions which are named as orbitals. So the subshells, orbitals. So which subshell will contain how many orbitals? There is a relation. That is, for S, for S subshell, the number of orbital is 1. For P subshell, the number of orbitals is 3. For D subshell, the number of orbitals is 5. The F subshell, the number of orbitals is 7. There is a formula, and that is, the subshells are identified by L, and L is actually indicating the magnetic quantum number. So for L equal to 0, we represent S. For L equal to 1, we represent P. For L equal to 2, we represent D. For L equal to 3, we represent F. So number of orbitals is actually 2L plus 1. 2L plus 1. So for S, you can see that it is 2 into 0 plus 1, that is 1. For P, L equal to 1, that means 2 into 1 plus 1. For D, it is L equal to 2, that means 2 into 2 plus 1. And for F, it is L equal to 3, that means 2 into 3 plus 1, 7. So this is the formula of orbitals, and it is represented from minus L to plus L. If I talk about the name of the orbitals, if I talk about the name of the orbitals, then it is 0. L equal to 0 for S. So that means minus 0 to plus 0. That is 0 only. And for P, L equal to 1. That means it is represented by from minus L to minus 1 to plus 1. That means the name of the orbitals will be minus 1, 0, plus 1. For D, L value is 2. That means it is represented, the orbitals are represented by from minus 2 to plus 2. That means all the 5 orbitals will be named as minus 2, minus 1, 0, plus 1, plus 2. For F, similarly, for F L equal to 3, so the orbitals are represented from minus 3 to plus 3, and of course the 7 orbitals will be represented as minus 3, minus 2, minus 1, 0, 1, 2, 3. So if I again consider the picture, keeping in mind about the concept of subshells and orbitals together, then the picture will look like something like this. It is n equal to 1, it has only one subshell. For n equal to 2, there are 2 subshells, S and P. For n equal to 3, there are 3 subshells, S, P, D. For n equal to 4, there are 4 subshells, n equal to 4, S, P, D and F. Now we have already drawn the subshells. Now we will draw the orbitals. So in S, the number of orbitals is 1. So it has only one orbital. So yes, don't mistake here, because orbit and orbitals, both of them are not same, they are different. So don't mistake, or don't have any misconception about orbitals, that orbit and orbitals are same. So just keep in mind about it. Okay, S shell will be having only one orbital, and P shell will be having 3 orbitals. As L equal to 1, so it will be represented by minus 1, 0, 1. In S, there is only one orbital. In P, there will be 3 orbitals. There will be 3 orbitals. And in D, there will be 5 orbitals. In S, of course, there will be 1 orbital. In P there will be 3 orbitals. In D there will be 5 orbitals. In F there will be 7 orbitals. So now comes the Pauli's exclusion principle. Okay. Before that, I would like to mention one thing, that each of these orbital will be having 2 electrons, which is part of this Bohr atomic theory. Each of these orbitals will be having two uh, 2 electrons. So it can be subdivided into 2 divisions again. But why do you why do we need this Pauli's exclusion principle here? The need of this Pauli's exclusion principle is actually, suppose at this n equal to 3, if we talk about the S subshell, it has 1 orbital, and that orbital is having 2 electrons. This orbital is having 2 electrons. So how can we locate this unit, this electron or this electron? These electrons are having the same principal quantum number because they are present in n equal to 3 cell, and they are also having the same magnetic quantum number because they are all, both of them are present as at S subshell. So their n value is 3 and L value is 0 because for S the L value is 0. So for this electron the n is equal to 3 and L equal to 0, and for this electron also the n value is 3 and L value is 0. So how can we differentiate these 2 electrons from each other? So for that actually we need Pauli's exclusion principle. What is that? Pauli says the electrons which are placed in a single in the similar orbitals, they can be differentiated by their spin quantum number. I'm repeating once again. The electrons which are present at the similar orbital, they can be differentiated by their spin quantum number. Pauli says if within an orbital there are 2 electrons, then if one electron is moving clockwise direction, another electron will be moving in anti-clockwise direction. So they can be differentiated using their spin quantum number because their principal quantum number is same, their magnetic quantum number is same. So what differentiate this 2 electron is their spin quantum number. If we consider about the anti-clockwise direction, then the spin quantum number, which is denoted, okay, I write spin quantum number is represented by plus half, and if the electron is moving in clockwise direction, then the spin quantum number is denoted by half, minus half. So, and the Pauli's exclusion principle says that no two electron within an atom can hold exactly similar energy state, quantum energy state. What does it mean? It means that suppose I am talking about this s orbitals for n equal to 3. I am considering this s subshell and I am talking about the orbital which is present in this s subshell. So in this orbital there are two electrons. If we don't have the concept of this spin quantum number, then we cannot differentiate these two electrons because they are having the same principal quantum number, they are having the same magnetic quantum number. So are they identical? Because we don't have any factor which can differentiate these two electrons from each other. So that is why Pauli came with his idea that if one of the electron is moving in clockwise in clockwise direction, then another one electron will be moving in anti-clockwise direction, and the anti-clockwise direction, in case of anti-clockwise direction, the spin quantum number is plus half, and the clockwise direction, the spin quantum number is minus half. So that differentiates these two electrons which are present in the similar orbital right now. So in the same way, we can differentiate the electrons, both the electrons which are present in exactly the same orbital. So that is why Pauli has said that no two electrons within an electron can hold the exactly similar quantum states, because if all the other quantum states get similar, then also it will be differentiated by the spin quantum number. So no two electrons within an atom can hold exactly similar quantum state. If all the other quantum states are equal for two electrons, then also it will be differentiated by their spin quantum number. So this is the Pauli's exclusion principle. So right now we are at the end of this Bohr's atomic theory for silicon atom. Now we will write the electronic configuration of silicon atom, and we will draw the model for exactly for silicon atom. So the atomic number is 14. So the electronic configuration will be 1s2, 2s2, 2p6, 2 to 4, 6, 10, 3s2, 3p, 2. So this is the electronic configuration of silicon. Now I will draw the model that suppose this is the 1s subshell, this is 2s, 2p, this is 3s, 3p 3d. So it has 2 electrons because 1s2, then 2s2, and 2s will be having 2 electrons. 2p6, it is having 6 electrons. P subshell is having 3 orbitals, and all these 3 orbitals will be having 2 electrons in each. So the 3 orbitals will be holding 6 electrons. So we can say the 2p is a field subshell, and 3s2, then 3s will be having 2 electrons, and the 3p will be having only 2 electrons. So 3p is holding 3 orbitals, and 3 orbitals have a capacity to hold 6 electrons maximum, but there are only 2 electrons. So this 3p subshell is unoccupied subshell. So now I will talk about the last portion of our lecture right now, that is half stability. Suppose you are carrying one bucket in your right hand, which is having a water of 5 liter, and suppose in case 2 you are holding 2 buckets, each one of these is half filled. Suppose in case 1 you are holding a bucket, half filled bucket in your right hand, and in case 2 you are holding 2 half filled buckets in your left and right, both the hands. Which of this scenario will be much more stable, or which will be easier for you to carry? I hope this will be the case when you will feel comfortable, because you are having same weight in both of your hands, so you will be much more stable than this scenario. The same here in the p subshell, in the 3p subshell, we are having 3 orbitals. Why? Because we know p means the magnetic quantum number is 1, and that means the orbitals are -1, 0, 1. So suppose we have these 3 orbitals, and each of these orbitals will be having the capacity of holding 2 electrons, but 3p is only having 2 electrons. So suppose these are the 2 electrons. So the 3p subshell will always try to be stable, because this is the natural phenomena of every object, that each and every one of us are always trying to be stable. So the 3p subshell will be trying to get stable, and for that it will accept an electron. If there is any source of electron present near the silicon atom, then it will accept an electron from that atom, and it will put it into the orbital, so that it gets it half stability. It gets its half stability. Half stability is much more preferable for an atom than to be unstable, from getting unstable, it is much more better scenario if I get half stability. So for that, actually, two silicon atoms which are having 4 electrons in their outer shells, they will share their 1 and 1 electron, and they will form a covalent bond, so that both of these silicon atom gets their half stability and get stable, get much more stable than getting unstable. So the half stability is the reason why the silicon atom forms covalent bonds. So actually this silicon atom will be sharing this electron with this electron of this another silicon atom, and it will complete its half stability, and again this electron this atom will do the same. It will share its electron with the outer shell electron of another silicon atom, and it will complete its half stability, and in this way both of these atoms will get stabilized. So by saying this, I am just ending this lecture right now, and I hope almost all the things I have told you is more or less clear to you. If you have any doubt, you can ask me in the comment section. I will definitely try to answer your question, and in the next video we will be discussing on the origins of the covalent origin of conduction band and the origin of valence band. We will be discussing on the energy bands and band diagram, bond diagram, on all those things. So just let me know that if you have understood all the things that I have discussed till now, and if you have any doubts, feel free to ask. You can ask me in the comment section. I will definitely follow the comments, and I will definitely try to answer your questions, all your doubts. So take care. Thank you. Bye bye.